So the third type is when the active medium is of solid state, and I listed here it for the third time, but this was the very first laser, as I said, that was operational. Usually it has a crystalline or glass rod which is doped with ions that provide the required energy states. It has a very simple architecture. It can be a very small size. I showed you how compact it was, because if you polish very nicely the ends of this glass rod, it can actually work as the mirror, the cavity mirrors as well. But it's not very tunable, because then it's that size, that length. These materials are pumped, usually optically, by another light source that can be a flash tube, and then the light coming from the flash tube is being absorbed by this active medium, and because there are always some losses during the process, we have to pump it with a shorter wavelength light than what we hope to achieve with our laser. Probably the most widespread type of laser is the diode laser. It is some electric, it works through some current. And in this case we have a recombination of electron and holes to induce the gain. Commercially available laser diodes have wavelengths from 375 nanometer to few microns, and they provide very low power laser light. This pointer has a diode laser inside, but they are very simple. You can see here the size, so you can actually use these diode lasers when you take plenty of a high number of them to pump other laser systems. And the last type of laser that I would like to mention is when the optical medium, the laser medium is an optical fiber. It's very beneficial, this form of using the laser, because you guide the laser into your fiber, you pump your fiber. You of course have to dope your fiber with some material that can work as a laser medium. But once you build such a laser, it's very compact, because many kilometers of fiber, optical fiber, you just wind up and then you put it into the corner, and you have an active medium of many kilometers of length. Light is already coupled into the fiber, so you can actually take it wherever you want to. These fibers can be made very high quality, and then the beam that you produce is also very high quality. Yeah, I already mentioned the compact sizes. So now, actually, there is a lot of effort in the industry and in research of improving these fiber lasers. At ELI, we are going to have some components of our laser system based on the fiber laser technology. So the first point that is required for a laser is, as I said, the active medium. The second is that we create population inversion, and I list here a few methods of pumping of population inversion creation. It can be an electrical discharge, so you have your active medium, the gas, and between the cathode and the anode you create a spark, and this discharge pumps the gas to the excited state. You can have a flash lamp where you take some light, and the active medium absorbs this light, and by this absorption it will be brought to population inversion. You can use an external laser source that can be a laser diode or other types of lasers to pump your system to population inversion, like in case of this fiber laser. But the laser diode diode can also pump solid state laser as well. And I don't have a picture here, but a chemical reaction can also feed the system into population inversion. And here I give you an example of when we pump with a laser, another laser. The pumping laser has a wavelength of 532 nanometers. This is a very standard architecture for short pulse system. So we use the frequency doubled beam of neodymium YAG laser, and we pump through these mirrors this component, which is denoted by X. This is the lasing medium. Whatever is absorbed will pump it to an excited state. Whatever is not absorbed will just be sent to a beam dump. So this is our primary laser, but we build a secondary laser from the other optical components. So we have here a mirror, which is the one end of the cavity. Light can propagate along this red line. And then this is the output coupler, or the other mirror of the cavity. So some light is leaking through. This is your laser that you want to use. The most part of the laser is being bounced back and being kept in the cavity. To make the laser light retrace its path, these mirrors have to be positioned properly. Also, these two mirrors are curved because you want to focus your beam into this active medium. And also, you see here two wedges that are used to manipulate the light inside the cavity to make actually the light bursts shorter, as short as possible. So you use a laser that is producing long bursts of light. These long bursts are pumping up the system almost at a stationary constant level of excitation can be reached by these long bursts. And then we build another architecture from optical components that can now produce very short bursts of light. So you use one laser and you create another laser, and you even lose some energy in the process because you cannot gain, you always lose something. Actually, you lose quite a lot that goes to the beam dump, but the laser that you produce will be better in some sense. It will have much shorter pulses than your original laser pulses. And this way it's worth putting all the effort into going from one laser to the other. So the optical resonator, or it's sometimes also called cavity or oscillator, is an arrangement of mirrors that makes the light bounce back and forth to increase the number. So it's a feedback loop. It increases the time the photon spends in the active medium for sufficient amplification. Also, the optical resonator defines the standing waves of the cavity. What it means is, basically, we want our laser to produce a very well-defined wavelength. So we want to have some very well-ordered property of our light. We can make an analogy with the simple pendulum. So you have a pendulum that it's defining the frequency of the oscillation, and this is what we want from our cavity as well. An ordinary oscillator, an ordinary pendulum, will lose its energy during its motion, and to keep it to a really sinusoidal oscillation, you need to keep giving it energy. So just this analogy I'm going to use for the laser oscillator. Here we have the light going back and forth in this this cavity, and it also creates very well-defined frequency. You can use the analogy of a string, and when you displace part of a string, it will create these harmonic resonant motions when the two ends are stationary, because it's held there, and you can oscillate the particles in between. So on the analogy of standing waves, this is what is happening in the optical resonator as well. So certain frequencies can be amplified. So we have a photon, it goes back and forth in the active medium many times, and you only amplify the photons that are in phase, that are coming together at the right time. So the time it takes for a photon to go around the oscillator defines the frequency, defines the wavelength of light that can be successfully amplified in a resonator. And this resonator needs to be pumped all the time to keep up the production of new photons. As I said, one of the mirrors is not perfect reflector. This is what we also call the output coupler. This is, in other words, a partially reflecting mirror. The reflection coefficient, depending on what type of laser it works for, sometimes just a few tenths of percent, sometimes 99.5. So it looks almost perfectly reflecting, but this small loss is enough for the laser to be applicable for certain applications. And then the light which is propagating through this mirror is what we're going to use in our experiments. So this is how the laser is being built. We have here the active medium and we have the two mirrors, and as I said, the distance between the mirrors, or the total path of the photon that it has to travel in one full round, determines what frequencies can be built up in such a resonator, and it corresponds to a comb of frequencies. The distance between two combs is determined by the total length. So basically, if c is the speed of light and d is the distance between the two mirrors, then 2d is the total length of the cavity, and this is the time, the inverse of the time that the photon takes to travel around the optical cavity, and this determines the position of these spectral lines. The active medium always has a bandwidth. Within this spectral range, it can amplify light. Outside, it cannot amplify because it doesn't have transitions, energy transitions. So these two, the gain curve of the active medium and this frequency comb, will determine what frequencies can be actually amplified in the laser. Sometimes we want to build a laser which doesn't have a frequency comb but has only a single very well-defined color. Then we can add further optical elements into our laser system that will get rid of most of the other frequencies, most of the other lines. These lasers we call spectroscopic lasers, and they are built for the purpose of giving only a very well-defined frequency. Sometimes it's more beneficial that we have a wider bandwidth of we have all the different frequencies amplified when we want to make a short pulse laser. So these are complementary properties of lasers. For each experiment, for each purpose, you can build your laser. This is what I'm trying to emphasize here, that whatever you want to do in terms of light-matter interaction, you can find a laser that will be suitable for your applications. I just give you here, again, a very rainbow-colored figure that shows you that if you know what wavelength you want your laser light at, you can choose a specific material that will amplify that bandwidth. This is now all from ultraviolet visible to the far infrared regime, and depending on what color, what wavelength you want, this picture gives you the material that you should use for your laser active material. So basically this is how we built a laser. And I would like to say a few words about pulsed lasers versus continuous wave lasers, because this is what the ELI lasers are really a very good example of, and this is where all the effort is being made to produce not a continuous beam of light, but rather a pulsed train of short pulses in the laser line. To illustrate it, I could say that this light, when I keep the button pressed, produces a continuous beam, continuous light, and when I keep it pressing on and off, it gives us a pulsed mode of the laser. But this is not very interesting, because what I can make by pressing the button on and off is are very low pulses. What we want from lasers is to be really short. So this would be an neodymium YAG laser whose dimensions I'm giving on this slide. And this is a long pulse laser. This is that in my previous example I said that we use these long pulses to pump the other laser system that gives us the really long pulses. So this laser provides bursts of light, and these bursts of light last 20 times 10 to the 19 seconds. So 20 nanoseconds long, I have a burst of light, and then there is nothing for 0.1 second. So every second this laser shoots 10 times, but during this shoot it's very short. So you can see that it's 10 orders of magnitude difference between the silence and the light itself. So if we slow down time, there is a burst, and then for a very, very long time nothing. There is a burst, and for a long time nothing. But if we use such a pulse train to pump a crystal up to excited state, since the lifetime of the excited state is longer than this we can keep the performance up. In one burst, we can have as high as 2 joules of energy, and as I said, this type of laser is shooting tens in each second. So these are the main characteristics that we use for a pulse laser: the pulse energy, the pulse duration, and how frequently the light bursts are coming. And how we can make short pulse lasers. So basically, if we have a single frequency component, this corresponds to a sinusoidal wave. This is very well known. So to be able to make short pulses and not continuous bursts, we need to add another frequency component. And this is what is called beating. If you have some background in physics, you might have heard that you have 2 sound waves that are close in frequency, and then you hear some increase and decrease and increase and decrease of the sound. So this is how it is very nicely illustrated. This is what happens with, that's a sound wave, and now we talk about light waves. If we have different frequencies and we add them together, we might reach intensity oscillations. This is the fundamental principle in producing laser pulses. And if we have a high number of frequency components that we can add up, we can make really short pulses and a long silence, and again a really short pulse. So to make short pulse laser, we need a broad bandwidth of the amplifier medium to support these short pulses. To build a pulsed laser, we need, as I said, a broad amplifier medium. We need the standard components, the resonator, the output coupler that every laser needs. And we also need something that we call mode locking scheme that modulates the laser light, that helps us to reach, because these frequency components, they have to come in phase. If they just come random, we are not getting short pulses. If we have a random phase behavior, this is what we get, a random fluctuation of light. If we have a well-ordered phase behavior, we get the short pulses that we require. So the broad amplifier regime and the bandwidths of these lines that is described by the length of the cavity will give us the possibility to produce these short pulses. And this modulation or phase locking can be achieved by different schemes. The modulator can be external to the cavity. So you notice this is one end of the cavity, other end of the cavity, and the leasing material. We can modulate the light externally to have a pulsed mode, or we can put this modulator into the cavity and either modulating the gain in the medium or modulating the losses of the cavity, we can actually reach this pulsed behavior. Another possibility is to modulate the pump, and also modulating the pump could lead to a pulsed laser behavior. And there is one direction in laser technology which is going towards shorter and shorter pulses. Another direction is to go higher and higher energies, of course. But what I'm going to concentrate on is the shorter and shorter pulses, because as I said before, this is why the ELI lasers are really superior to many other, because of the short pulse duration. Here you see what progress has been made. So the first laser was demonstrated in 1960, and then since then new laser materials has been discovered and used, and improved dispersion management has been used to now get to a fundamental limit. In the visible region, the wavelength of light determines how short a light burst can be. And we are at this limit. So we are now producing routinely light pulses that only have a bit more than one oscillation. And you cannot have shorter than at least one oscillation, but because then it's not an oscillation anymore. So we are into at the limit. The limit is this dashed line, and these are lasers that are now available on market. Why do we want to make shorter pulses? Because it's, well, for us physicists to start with, because this is a challenge. You want to be shorter. You want to be able to show that you push to the limits. But additional to that, people using lasers want short pulses because they want to concentrate the energy of all the light into a very short time, because then it's more intense. So we have a higher concentration. The other is, when you study the dynamics, some very fast process, then to be able to freeze the process to snapshots, the shorter your flashlight, the faster process you can study. So just an example of how we freeze the dynamics of the system. I'm telling you that if you want to study a process, a dynamical process, so motion, on the millisecond time scale, you can use mechanical shutters. Basically, this is the example that we keep using when we talk about studying dynamics. Back in 1878, some people with plenty of time and just drinking, I don't know, wine, beer, sitting at the horse race, nothing to do, they were discussing whether a horse, when it's galloping, would be in a state that all four legs would leave the ground at the same time or not. And this process is too fast for the naked eye. You cannot see it. So it was just a debate. And they asked an engineer to make a decision. So this engineer actually designed a way of putting, I think, 20 cameras on the way, and they were synchronized to shut at different time instants. And this is how this famous photo set was obtained. And then you can really see what is happening during the motion by freezing it. So this is the analogy that we use when we discuss about what molecules are doing, because it's easier to understand. So basically, fast processes on the millisecond range, 10 to the minus 3 second range, can be observed when we freeze the motion by a mechanical shutter. Somewhat quicker events, like the formation of the structure when a drop of milk is dropped into a liquid surface, can be studied by an electronically synchronized flash. So what you do, you keep your detector open all the time, because this quick you cannot open and close something mechanically. So you just have a film there standing, and you have a very short flash which is synchronized and illuminates what is happening during a very short time. So you have a somewhat faster motion, you freeze it with a very short flash. What you need is, you need to be synchronized, because if you are flashing before the drop reached the surface or after, you don't see anything, but you can synchronize it, and then during this very short time that you have your flash for microsecond, nanosecond regime, you can freeze that process. But there are processes that are even quicker than that happen on the femtosecond and on the attosecond time scale. You need to use something that is even even shorter bursts of light. So this is why lasers are being used, and for the synchronization we use a pump probe arrangement. What is happening in a pump probe experiment is that you have two pulses that are synchronized at their burst, and then one is being sent on a somewhat longer somewhat longer path, and this longer path results in a delay between the two pulses. And since light travels 0.3 microns in each femtosecond, moving this retroreflector on a sub-micrometer scale gives you a delay of femtosecond range. And you initiate a process in your target with your clocking or pump pulse, and then you send the second light pulse in to check what has changed. This is the scheme for a pump probe experiment. Here you see a pump probe experiment where the first pulse started some blow-up, some disintegration of a protein molecule, and the second one was actually an X-ray pulse, and X-ray diffraction has been used to map out how the individual atoms in this protein molecule moved during the process of the blow-up. I think it's not coming to a real surprise, but it's nice to put it into words that the smaller the element that you want to probe, the faster it can move. Just to give you an example, the smaller the object, the faster it can move, so the shorter the light burst, the flash burst that you need to employ. So the sub-picosecond range, so the many femtosecond range, is that you use to study atoms in molecules and solid. But if you want to look at smaller constituents, electrons, and to see how they behave in nanostructures, molecules, or atoms, then you reach the sub-femtosecond or the attosecond regime. The electron, if we imagine electron as a particle which is circling around an ion, one electron in a helium atom circles the atom in the first orbit in 100 attoseconds. So this is the time scale that we are targeting here at the ELI infrastructure. A somewhat bigger system is a molecule. Biologically relevant molecules can also be studied. Here I just indicate that signal transferring proteins plays an important role in medicine, so this is something that can be examined in pump probe schemes. This movie in the bottom shows that we have here again a complicated biomolecule, and one end of this biomolecule there is an electron excess, and then this electron distribution actually leads to a structural modification of this whole molecule. And these are things that we are about to study. So we want to see how an electron, missing an electron or adding an electron to a molecule will affect the functioning of this molecule. What is the dynamics, so how it all happens and what it will result in. This change in electronic configuration, so this additional one electron, or just you ionize this molecule, it can be the effect of some radiation, or it can be an effect of a drug, and then this structural change, it can be either indication of illness, so you use diagnostic to study, or it can be actually the sign of curing an illness. So the behavior and the properties of this molecule might depend on such a simple thing as removing one electron from the molecule from one end, and this is now the focus of attosecond science research, to see how the electron distribution happens following this initial change in the electron configuration. As I said, the other reason why we want to produce short pulses is to concentrate the energy of light into this very small burst. So now I show you a different example of a laser pulse. This is the femtosecond light pulse you see here. It is producing 35 femtosecond pulses. The repetition rate is the same as the previous example I gave, because this is now the short pulse laser that I'm pumping in my previous laser. So I have the same repetition rate. And I can have, of course now I have a smaller energy in a single pulse because I lose a lot. But since I'm decreasing by 5-6 orders of magnitude the duration of this pulse, I still get a more intense burst of light. I can describe the concentration of energy either by describing it with fluence, when I just take the energy and divide it by the cross-section of the beam, or I can look at the power of the light, which is also another dimension that I'm concentrating my light energy, taking the energy and dividing it with the duration of the pulse. So this is spatial concentration, this is temporal concentration of light energy. Or when I talk about the intensity of light, this is really, I take energy divided by time and space. So this is what describes really the strength of the light field in this laser pulse. Intensity is related to the electric field strength. So I take the input energy, see how much I can concentrate it both in space and time, and then it will give us what is the strength of the electric field. So my example of this, now I have 20 femtosecond, in the previous slide it was 35 femtosecond. It depends on how good you are in building your laser. And here I show you that it's only 35 millijoule that I have in a single pulse. In the pumping laser, I had 2 joules, so I lose a lot, but still the intensity of the light that I'm producing is many orders of magnitude higher in this shorter pulse configuration. And when talking about pulsed lasers, we have to make a distinction between peak power and average power. Peak power describes what is the strength of the field during the pulse. Here I take the energy per pulse and divide it by just the duration of the pulse. And this will tell you how strong the field is at the time when it's present. So it tells you how strong the interaction is that you can make between your laser pulse and whatever you put in front of it. The average power, is you take a long time and you see how much energy is being supplied by the laser during that long time. So for the long time we take 1 second. This laser shoots 10 times every second because the repetition rate is 10 Hertz. So here we get the average power. This terawatt is 10 to the 12 watts, so this is, as I say, we concentrate the energy of light to this very short time. If you want to get some comparison, we have a nuclear power plant here in Touch that supplies a considerable amount of portion of the energy, electric energy that Hungary is using. It is supplying gigawatts, so 10 to the 9 watts. Here I told you that in the building we have a terawatt laser, which is providing us with 10 to the 12 watts. The main difference between the two is that this is continuously available. Watt is joule per second, so it's a bit misleading to compare two values that is available constantly or only during a very short time. So this is, in a sense, we get from the electricity we get some energy out, and then we concentrate it very strongly to be able to study very strong, very intense processes. And although we have these terawatt pulses, and I say that this is many orders of magnitude higher than what the nuclear plant is providing, I don't need the nuclear plant to feed my laser, because the energy that my laser system is requiring is related more to the average power. Of course, there are plenty of losses, so it's 1,000 times more, or maybe 10,000 times more, but still this is small compared to the concentrated energy that I'm producing with my laser. And the ELI super laser is going to be able to produce even 10 to the 18 watts. So we are going further with the available peak power. And I have already touched this subject very briefly, but here I have a numerical example. So the intensity of light is related to the electric field strength, because light is electromagnetic wave, so there is an electric field strength which is oscillating. And the intensity is the quantity which is proportional to the E squared, so the electric field strength squared. So in our university lab laser pulse, we focus it down to 100 micron diameter spot. Then we have an electric field in that laser spot which is 10 to 11 volts per meter. This is just a number, but if I tell you that in comparison, the Coulomb force that keeps the electron to an ion is also the same order of magnitude, 10 to 11 volt per meter. So basically we can produce at this laboratory the same strength of electric field that would bind an electron to the atom. So with our laser light we can ionize this system, or we can do all sorts of funny things. We can put a molecule into the laser light and we can in a way break any of the bonds that we choose to. So you have a complicated molecule and you want to break it here, there or there, and with the proper laser pulse you can do it. And you can do it because you have enough field strength, and also you can do it, it has some dynamics to it to break the bond that you have chosen, but you can tailor your pulse accordingly. This is possible. Just a more popular description of the field strength that we have. If you would take the sunlight energy that falls onto the Earth, the total amount of light that falls onto Earth, and you would focus it down onto a palm size, then you would reach 10 to the 14 watts per square centimeter. In my previous example, I said that we have 10 to the 16 watt per square centimeter. So this is really a huge density of light energy that we are producing here. And at ELI, what is going to be available is 10 to the 25 or so watt per square centimeter. So this is really whatever you put into the way of this laser pulse, it will be evaporated. So the question is not what's going to happen if I shine my laser on this or that. The question is how will it happen? And this is why we need the short pulses to be able to study the very beginning of this blow-up procedures. So coming back to lasers in general, the properties of laser light that I have told you at the beginning of the talk is monochromaticity, coherence, collimation, and the good focusability that make a distinction between laser light and ordinary light. And I'm going to give you examples of why these properties of the laser light are really beneficial to be used in medicine.